love the chase and the hunt, and I set the pace when I'm running. I always
Namaste Friends. So today is chapter 94 in the entire Python. And the last 2 days we saw about graph. Okay, so it went for 2 lectures and you also saw the breadth and depth of the 2 lectures. So today also will be a 2-part series, and this is called spatial data. This is SciPy chapter 6 in the SciPy, and this is spatial data part 1. So the spatial data, working with the spatial data, refers to data that is represented in a geometric space. So this is a space, and the data here or the spatial data is for the spatial data. So the points in a coordinate system, all these things are here. We deal with spatial data problems on many tasks. Example, finding if a point is inside a boundary or not. So the SciPy actually provides a module like everywhere, which has functions for working with spatial data. So this is like if a point is inside the boundary. Say, suppose if this is the boundary, whether the point is here or here. So this is outside the boundary, this is inside the boundary. Okay, so this is how, like, even the coordinates, x coordinate, y coordinate, z coordinate. So this is how we actually find. All right, triangulation is basically like this, right? A triangulation of a polygon is to divide the polygon into multiple triangles with which we can compute an area of the polygon. A triangulation with points means creating surface composed triangles in which all of the given points are on at least one vertex of a triangle on the surface. One method to generate these triangulations through points is the Della Uni open and close parenthesis triangulation. So if I have this polygon, or if I have something like this, any kind of a shape, if I actually put every triangle there, triangle there, triangle there, it is called triangulation. And I can also find this using this method. Okay, all right. Like always, let's actually create a triangulation from the following points. So I can actually take this and let's actually, go through this code once, right? So if you see, these 3 lines is to make our compiler able to draw, which is import sys, import MATLAB, which matplotlib, which is a MATLAB, matplotlib. And then we are using aggregator. We are importing numpy as numpy, and this is where the spatial data is coming in. And then we are importing the Della U and NAY. So where is this Della U NAY coming? It's in the triangulation. All right. And we actually say plot, and then we give an array, and then we say simply sizes, and then we say all these things. We say a color, and then we say plot show, and then we say, like, to make our compiler able to draw, we say plot save figure this buffer, and then flush. Okay, so this is what we do. So let's see whether it actually gives us anything here. It is not able to do a matplot, is currently using aggregator, so so it cannot show the figure. This cannot show the figure, but usually it should be showing the figure. So this is out of stream, so this Jupyter is not able to show the figure. All right, but there is something called as a convex hull. The convex hull also is more or less the same thing. So if you actually take this, I'm not sure, I don't think even this is going to show the figure, because we're even flushing it out and stuff of that nature. This is also not going to show us a figure. Okay, but this is also another way of actually showing it. Maybe this matplot use lib, since it is not there, maybe if I just keep this, and if I just run this, I think it's still the same. It'll be still the same. Yeah, so bad operand for unary. All right, it's still the same. So let's actually do here, we have the same, and we have a big array, and then instead of the Della UNY, we actually use a convex hull, convex hull, and everything is the same. And again we say, like, plot. Okay, so if we actually do again, I don't think it's going to show, because or what I can do is I can actually, now I can actually try running this, but still, this is not showing me. Okay, so this is not showing me. All right, fine. So there is something called as a KD trees. The KD trees are a data structure optimized for the nearest neighbor queries. So I have here, and then I have a nearest neighbor query. So this is how it is optimized. In set of points using KD trees, we can efficiently ask which points are nearest to a certain given point? Okay, we can efficiently ask that. The KD tree method returns a KD tree object. The query method returns a distance to the nearest neighbor and the location of the neighbors. All right. So this KD tree, we can actually find how it is. So this is what we import the KD tree, and we need to find the nearest, right? So this is what the KD tree, right? So if you actually run it, it is 2.2. So what the KD tree does is data structure optimized for the nearest neighbor queries. In a set of points using the KD trees, we can efficiently ask which points are nearest to a certain given point. The KD tree method returns a KD tree object. The query method returns a distance to the nearest neighbor and the location of the neighbors. Okay, so it is optimized for the nearest neighbors. Okay, optimized for the nearest queries. All right. So we can actually efficiently ask which points are nearest to the certain given points. All right. So this is what it is. I know the first two things for the Della, UNY, and the convex cell, we were not able to produce an image, but at least we saw the KD trees. And in the series of in the next lecture, we'll be seeing about the distance and different distances. I think it's a good point to stop here. I trust you would have actually seen my lecture, understood it, and probably enjoyed it. If you have any questions, kindly contact me. I'll actually try to explain to the best of my abilities. Like always, I'd like to thank two persons. One is you for giving me a golden time, and the other is my wife Jayashi following me to follow my passion. Till we see you next time. Thank you, take care, and cheers.